everyone, welcome back to today DWF YouTube channel. This unusual introduction on my video is to celebrate the important milestone of my channel, reaching 1,000 subscribers. Thank you all my viewers, all my subscribers, and a big special thanks to Adrian of Adrian Digital Basement YouTube channel for linking some of my videos on his own videos. That has helped a lot to reaching this important milestone. So let's go to the topic of this video. On a recent video on Adrian Digital Basement channel, he demonstrated the use of NOP Generator for the 6502 to troubleshoot an issue on Commodore 1541 floppy disk drive, and it did a very good job explaining how the NOP generator works and how to use for this particular troubleshooting. So I thought I will make kind of a follow-up video to explain other uses and different approach on the construction of simple NOP generator sockets for the 8-bit CPUs. By the way, if you haven't seen Adrian's video, please go watch it before continuing this one, because I will give some information for granted in this video, and I think he did a really great job explaining what an NOP generator is supposed to do and how it works. So you find the link to Adrian videos in the description. What we see in this image is a typical 8-bit microcomputer architecture. Explaining how all works goes far beyond the scope of this video. What we have to understand basically is the CPU, when the CPU wants to communicate, read some bytes, write some code or data, or access I/O ports, it just emits an address on the 16-bit address bus, and from this address, the address decoder is programmed in a way that it knows where the ROM is supposed to be in the address space, the RAM is supposed to be in that address space, and various I/O chips supposed to be. So based on the address that the CPU puts on the address bus, one of these blocks is selected. And when a block is selected, it means it can either write data, an 8-bit data on the data bus, or read what the CPU wrote on the data bus. And that depends on the state of the control bus signal, in particular the read-write signal from the CPU. So what CPU does from the moment we start applying power to it and lift the reset signal, the CPU starts reading memory location from a well-known memory location. For example, the 6502 starts reading hexadecimal FF, FC, and FFFD. It reads location, get a byte from that location, and every byte corresponds to an instruction. And for example, in the image we are seeing the 6502 instruction set, and in the OP column we have hexadecimal numbers that represent every instruction that is known to this processor. And every instruction does something like make some logical operation, adding 2 bytes, or subtracting, or deciding if to jump on another location, and when where to jump, and so on. There are many instructions like this. So the CPU
just do these basic operations in sequence very fast, but it's just this operation that he can do. So let's suppose that we are debugging a not working microprocessor unit, which could be a computer or 1541, an arcade game, whatever else with a similar architecture. And let's suppose the address decoder has some faults. The address decoder in the actual circuit may be a certain number of different TTL chips connected together, for example. What may happen is that the ROM never gets selected, for example. So when the CPU starts executing code, it will go to ROM location for reading instructions, and the ROM never gets selected, so the data bus basically reads like noise, and the CPU just get confused doing nothing, or get stuck on illegal instruction or something else. Another thing that may happen is that the address decoder is bad in a way that it selects more than one part of the chips at the time. For example, one I/O chip may be always selected, or RAM and ROM can be selected together. What happens in this case is that more than one chip go right in the data bus, and the data bus basically also get trashed because the signal have no meaning. It's also noise, kind of noise, and so the CPU cannot execute anything. Another thing that may happen on an actual microcomputer system is since there are many chips that need to get the same address lines from the CPU, what happens is there are other chips called buffers that just copy the inputs to the outputs. So the CPU just drives the buffer inputs, and buffer outputs go to all the other chips. So what happens if address buffers have some faults? What happens is that the actual address that goes to the ROM or the RAM or whatever else is not the same that the CPU is putting on the address bus. So the CPU is going to access something, and what happens is a different location gets selected. So the CPU cannot execute the code in the same in the right order, or not executing code at all, because always the same location gets selected, for example, or just random location gets selected instead of the correct ones. So this is another possible fault. So if we want to debug address bus, let's suppose that we can convince a CPU, in this case the 6502, to always execute this particular operation, which is called NOP, for no operation. What will happen is that it would read this operation, do nothing for 2 cycles, actually 1 cycle, because the first cycle is spent to read this operation from the data bus, and the second cycle is spent doing nothing. Then the CPU will increment the address bus content, read another no operation from the data bus, and cycle incrementing the address bus forever. What happens when it reaches the FF hexadecimal location is that it starts again incrementing from 0. So it will loop through all possible addresses forever, and we could debug the address bus buffers and decoders easily. What Adrian did on his 1541 is to hardwire data bus pins on ROM or RAM socket to the hexadecimal EA configuration, by tying the pins either to VCC for make a 1 or ground to make a 0. But one problem with this approach is that some other components on the data bus remain connected, like in this 1541 the two 6522s are soldered on the board and they cannot be removed. This means when the CPU reaches their addresses, they will connect to the data bus and output their register contents. So the NOP generator should not fight too hard with other chips driving the data bus. That's why, as you've seen in this picture of the video, he had to use resistors on each data line to avoid ruining damaging other chips that might be driving the data bus at the same time. Of course, in this case, Adrian had no other choice because it's 6502 on that 1541 board what was soldered directly on the PCB without a socket. But a more general approach is to take a 40-pin socket, cut the data pins, and hardwire the data bus of the CPU directly to the EA configurations. And this is always a good thing to have, and because, for example, Apple II always has socketed 6502s, as I seen on the board where I worked. Commodore PETs also have socketed 6502 usually. For example, Atari Asteroids arcade board also have that, the 6502 socketed. I know because I'm working right now on Atari Asteroids boards, so stay tuned for more arcade videos in the future. And so what we do is also cut the IRQ and NMI pins and connect to the VCC because usually on a board the CPU must first initialize the IRQ or NMI sources, but that's not always the case. And what happens if we are running a NOP generator and we get an IRQ or NMI, is that the CPU will stop executing the NOP sequence and make some writes on the stack area because it wants to save the current content of the program counter, and also write on the stack the content of the status register on the processor, and finally jump to a location that is contained on a couple of locations in the FFF address space, and we'll start executing the NOP over and over again. But there are two possible problems. First is the CPU will write, so will compete against the NOP generator. So we would need to use resistors again. And another problem is it would not cycle through all the address spaces because it could get enough interruptions before completing a whole address cycle from 0 to FFFF and back. So we could never see the whole address space scanned in this way. So the NOP generator must also cut all external interrupt or non-maskable interrupt sources. Just a little note on the kind of sockets I use for these tasks. The round pins one have the pins shaped in a way that can be cut and still leave enough of the pin to solder wires to make the connection, the required connection for the NOP sockets. They don't usually touch the other socket, the CPU socket in the equipment we are using the NOP generator. But if they do, we can always add a little bit of plastic tape, insulating tape, and make the data bus pin not touch the original socket if required. As a practical demonstration of the NOP socket, I'll try it on my Commodore PET 2001 motherboard, and we see here a little part of the schematic of this board, where we can see some of the address lines going through buffers, A11, A10, A9, A8, A7, and so on. And so we will check that we have input signals on these buffers and output on the other side. In the same motherboard, we'll also check the main address decoder, which takes address from the CPU from A15 to A12, so 4 addresses, and selects one of its 16 outputs. Of course, these 16 outputs must not be low at the same time. Only one of these 16 addresses outputs is low at given time, and it will scan all these outputs one at a time in sequence when the NOP generator is working good and this decoder is working well.
Okay, so this is the demonstration setup for the 6502 NOP generator, and I'm using my PET 2001 motherboard that I still didn't install in the original case, but hope shortly to do that. Anyway, so as we said, the NOP generator should be used after checking the basic working of the power supply, clock generation. If you have an oscilloscope, you should check that there is no evident address bus or data bus conflict, so signal look normal, and we just want to try debugging the address distribution and the address decoding logic. So first of all, we inserted the CPU over the NOP generator socket that we have seen in the CPU socket of the board we are troubleshooting. Of course, this 2001 works well, so I don't expect to find any problem, but I'll be showing the use of the logical probe, which is a tool that is not very expensive, that anyone can buy, even new. This is an old probe, but the new ones work just the same. And I will also show the frequency we measure on the frequency counter, so you can see what kind of signal you have to expect. So first thing first, let's check again that we have a clock input on pin 37. Pin 37 is the input clock on 6502, and we do have Then we have to check if the 6502 is working well. We have on pin 39 we have clock output, and we do, and on pin 3 another phase of the clock output, and we do. So let's see the frequencies. So input clock should be around 1 megahertz. Pin 37 again, 38, 37, yeah, 1000 kilohertz, so it is on 1 megahertz. So same thing we should measure on pin 39. Yes, indeed. And on pin 3, same thing. They are inverted phase, but the frequency is always 1 megahertz. Now, on a healthy, I will show directly the frequency. On a healthy 6502 with NOP generator, we have on pin 7 the sync signal 1, 2, 3, 4, 5, 6, 7, which is half the clock frequency, so 500 kilohertz. Pin C, the sync pin is pulsing whenever the CPU is executing one instruction. So we have seen the NOP instructions actually takes 2 cycles, because the first cycle is the fetch memory read operation. So the CPU reads a memory location, which in this case always reads like EA hexadecimal, which is the NOP. And on another cycle, the CPU is executing this instruction, which means it's just wasting one cycle. So sync pin indicates when the CPU is executing one instruction, so it's half the clock frequency, because the first half is the fetch, second half is execution. So far so good. Now we can check the address pins of the CPU. The first address 0 is on pin 9. 1, 3, 6, 7, 8, 9 should be this one, and this is 250 kilohertz. So this is toggling every 2 cycles between 0 and 1, so it makes frequency of 2050 kilohertz, 250 kilohertz, I mean. This is the fastest toggling address bit, because it's the lowest address bit. All the other addresses should toggle at half the frequency of the previous address. So if we move to address 1, we should find half the frequency, and let's move 125 kilohertz, which is correct. Moving again half that, 62.5 kilohertz, I mean. So this is good. Okay, half again, moving one address. This is half of 62 is 31.25 1 or 0 well kilohertz. So let's move again half that, and again if we move half that. So if we jump to address 15, which is on pin 25, 21, 22, 23, 24, 25, this is the slowest. Yeah, a bit too slow. Let's see if I can get more resolution. It's counting. So it's always in kilohertz, but is 100 and 7.6 Hertz, I think. Yeah. So the CPU is going through all the addresses 7.6 times a second, which is not very fast, but even not very slow, because it's counting from 0 to 65,000 and more, and then coming back to 0. So it's making 7.5 complete address cycling every seconds. And this is the slow address, the address 15. Now, as we have seen, what we want to check is the address buffer. For example, like in the previous picture I've shown, address 11 is coming to UE5 on pin 1. So UE5 is 2, 3, 5, pin 1, 2, 3, 4, 5, this one. This is too slow. Maybe we check that with the logic probe instead, which is faster. We just want to know if the address are toggling and the buffer working. So as you can see, the logic probe on pin 1 is toggling. So A11 then goes to pin 2 of the same chip. Oh, that's toggling because of my touching the probe with my finger, but yeah, okay, that's a good. Pin 2 also works as expected, the buffer is working. Then it enters pin 3, again the same address, of course they are connected together, and exits on pin 4. So this buffer is working. We can check other buffers, but it's the same thing. You check the input after you have checked all the addresses are generated correctly. You check the input of the buffer for the signal reaching the input, and then the output of the buffer. If we check with the oscilloscope, we will find the same exact signal on the input of the buffer and on the output. For example, we have A9 entering pin 9 of E4. E4 is this one, pin 9, 8, 9 is this one. So the address is coming to the input of the buffer, then it exits from pin 8, which is this one. So it's toggling again. So this buffer is working. Then on the next picture of the schematics, we have seen the address decoder with these which is UG2, where are you? This one, okay, this is UG2. So as we have seen on the schematic, addresses are coming to pins 20, 21, 22, 23. So this is 14, 23, 22, 21, 20. Yes. So the decoder is getting all the addresses, and we should find on pin 1 to pin 17 all the possible outputs that should be all toggling. Yeah, toggling. And if we check the frequency of these pins, they should also have all the same frequency because they are evenly spaced. If I just make a good contact, yeah. And it's about evenly spaced, but the problem with this signal is it has a very low duty cycle, because it's almost always high, and it's toggling low for just brief period of the address space. But anyway, the concept I want to show is this one. The address decoder has a lot, some number of outputs, and all outputs should be toggling with NOP generator installed. This one is toggling too. Well, I know the board is working, so every output is actually toggling. Okay, just find another one, and it's toggling too. So okay, that's what you can check on a board. If you find a stuck output on a buffer, or an address decoding not giving an output toggling, well, you have found a problem on a board. So this can help. Of course, on the board you can also check the ROM enables. All ROM enables should be toggling. All the RAM enables should be toggling in this moment. So you can check a whole lot of things with an NOP generator installed. It's a good way to find hidden problems in the logic board. So the same thing would be on a Z80 board. I have a few also, but would show almost the same thing. So let's go. Let's talk a little bit more on other possible processor that can use NOP generators. One other processor that cannot use it. Let's see what I mean.
Of course, we can make NOP generator sockets for other processor like the Z80. We see in this page the NOP opcode is all zeros on this processor, so the NOP socket is a bit simpler. And this is the pinout of the 40-pin Z80, and also in this processor we need to cut the int and NMI pins and tie them I to prevent any external interrupt reaching the CPU. And we notice that the data bus pins are not in any order at all, but since all the data lines need to be tied low, it's a simple task anyway. And this is my rather abused NOP Z80 socket for NOP generation. It's simpler to make than the 6502 actually. And on the same principle, we could make, for example, a Motorola 6809 NOP generator. But we cannot, for example, make an NOP generator for the 6510. And let's discover why. This is the first page on the 6510 microprocessor data book. And what it says is, an 8-bit bidirectional I/O port is located on chip with the output register at address 0001 and the data direction register at address 0000. What it means is, when the processor accesses either the 0001 location or 0000, it will not read or write from the external data bus, but it will access the internal port. So we cannot change what the processor reads on these two addresses externally. This is the memory map of the 6510, always from the official data sheet. And we see that the two I/O port register are located at the bottom of the memory. And so the question is, what we find after reset on these two locations? Well, the datasheet says these two locations are initialized with the content 0. So both these two memory addresses will read with a 0 after the processor has been extinct the reset procedure. Now the next question is what the processor do when reading add 0 as an instruction code. And since the 6510 is actually a 6502 core with the added I/O port and some other minor things, then 00 is the BRK or break instructions. What it does, description says operates like an interrupt. The program counter is pushed on the stack. Then the status register P means it's pushed on the stack too. The contents of memory location FF, FE and FF are then deposited respectively in PCL and PCH. What it means is it reads these two locations and initializes the program counter, which is what we find on the address bus after that. The value of P stored in the stack as the B flag set to 1 to differentiate from BRK from an IRQ. So basically the BRK is a soft IRQ, and it will happens anyway when the processor reads at 0, it will do this. So it will write 3 times on the stack area, 2 times to store the program counter, and a 3rd time to store the processor register, the status register, as it does with a normal IRQ. So basically this is an IRQ processor-wise that we cannot avoid in any way. So with this rather sketchy image, let's try to understand in details what happens. So when we first apply power and the reset signal is lifted, the 6510 reads the 2 locations FFFC and FFFD. Since we forced the data bus to the configuration EA, it will jump to EA hexadecimal and start executing NOP there, incrementing the address counter and reaching FFFF. Then the address counter wraps to 0000, and we have seen that it reads the data direction register there that is initialized to 00 at reset, and so the 6510 executes BRK break instructions. And what happens, it does the 3 writes on the stack area that we have seen on the data sheet. So first of all, it turns the data bus to write. So if we haven't put the resistors in series on the data lines, it will destroy itself instantly because it will try to drive the power rails and it fails. So if we want to attempt NOP socket on the 6510, we have to use resistors at least 330 ohms on each of the data lines to the either VCC for the 1 or ground for the 0. So this is the first problem. Then after writing 3 bytes on the stack page, it will start writing at 01FF, then going down on every BRK, decrementing by 3 until reaching 0100, then wrap around to 01FF again. So with enough cycles, it will scan all the page 1 memory area. But then after these 3 writes, it will read the location at FF, FE and FF, and again it will read EA, and will jump again as it did at the reset moment, and the cycle repeats forever. So it's not very effective in scanning much of anything. It will just go from EA to FFFF, read at 0 page location, just one, then write to eventually all the page 1, nothing else. So it is not very effective as a diagnose tool. And so this is almost all for first scratching the surface on NOP generators for diagnosing 8-bit CPU systems. So I hope you enjoyed this video. I hope you find it informative, and if you have questions, leave the questions in the comment, and I will be happy to answer if I can, of course. And thank you for watching.